Good morning, everyone. If you could just indicate in the chat box if you can hear me. Okay, thank you. I am just uploading just the lecture slides right now, so I'll do that. So basically, I did one change to the integration slide that I uploaded for last lecture. So please use the latest version. And I'm uploading today's lecture in the folder, I guess, on Canvas, so that basically you have a PDF of today's lecture. Okay, so let's go to our screen here. Okay, so what we're going to do is continue in the coding of integration, but I guess what you did before was using integration to code a merge or a diverge, merge, diverge, and weaving sections, which was freeways. So the only thing that I'm going to add here, and so we're not going to actually do a hands-on demonstration of this, given that you've already coded with integration. What we're just going to do is go over how you can code traffic signals in integration and describe that. So I guess just as a refresher, there are different types of modeling approaches of traffic. Does anyone remember what they are? What are the different types of modeling approaches that we have for traffic, for modeling traffic? So Jake mentions green shields. So green shields is a traffic stream model, but it's not a way. So basically a green shields model can be converted into a car following model, or it can be a macroscopic fundamental diagram. But the question is, should I model, let's say I want to model with green shields. Should I model it using the fundamental diagram, or should I model it as a car following approach? What is the difference between those two? Any thoughts? So the difference would be if I model it as a fundamental diagram, that's called what we call a macroscopic approach. And macroscopic means that we are modeling the traffic as a compressible fluid. So it's compressible because as the density of traffic, as the level of congestion increases, the density of traffic increases, which means they become closer together when you add more vehicles onto the network. And then when you remove vehicles from the network, the density decreases, which means the spacing between vehicles increases. So it compresses when it's congested and decompresses when it's uncongested. The flip side of this modeling approach is what we call microscopic. Microscopic means that we track every individual vehicle, the movement of every individual vehicle. So we have to track it, what lane it should be in, and if it's in this lane, what speed should it be traveling at, and how should it get from its point of origin to its point of destination, and so forth. So integration fits into that category of microscopic models where we track individual vehicles anyone remember how often we track the movement of every vehicle? Anyone remember how often integration tracks the movement of vehicles? So it tracks the movement of vehicles every decisecond, so 0.1 seconds. So we're tracking every vehicle as it moves through the network every decisecond. And I guess the unique thing about integration is it is computationally very, very efficient. So for example, we were modeling the greater Los Angeles area, 3+ million travelers that we were tracking. But if we were modeling the downtown area of Los Angeles, which was around 500,000 vehicle movements that we were tracking, it was actually faster than real time. So basically, if you wanted to model 2 hours of the traffic demand, it would take you less than 2 hours to model those 2 hours. So it's actually very, very efficient. And if you compare that to other models, other microscopic models, it is much faster than the other microscopic models. So has anyone here used any traffic modeling tools, I guess, working in the consulting field, anyone? And if so, what model did you use? So I know one person, I forget who it was, had said that they had used Synchro to optimize the traffic signals. Did you use the modeling tool with Synchro, the person who used Synchro? So Jake mentions he used Synchro. Did you use the modeling tool with Synchro that actually tracks the movements of vehicles, or did you just use the Synchro optimizer? So I guess it's called Sim Traffic, is it called? The modeler that they have, Jake? So they have, so basically they have what they call Sim Traffic, which basically after you optimize the signal timings, you can model the traffic using Sim Traffic to look at what impact those changes in the signal timings have on the traffic stream behavior, which is what you're going to be doing for your project. So, but instead of using Sim Traffic and Synchro, we're going to do the computations by hand so that you learn the logic behind how you compute the signal timings. And we're also going to do the modeling with the integration software. Has anyone else used any traffic simulation software? Anyone in the class? So it seems no one has. Okay, so, and I should mention that integration, we provide it to people for free. So even after you finish this class, and we keep on updating it, if any time you would like to reuse integration, you can just send me an email and we would forward you the latest version of the software as it stands at that point. And it's for free for anyone to use in the world. So our philosophy is let people use it for free, and so feel free to contact me anytime if you'd like to use it. Basically, we mentioned this, that if you want to model a stop sign, you give it the signal number as being 10,001. If you wanted to model a yield sign, you made it 10,002. If you wanted to allow right turn on red, you would make the signal number. So in file 2, you have, when Saif described to you, you had 3 entries: the signal number, the phase number that would discharge during the first phase, and the phase number that would discharge during the second phase. So let's say you had the vehicles could discharge during phase 1, which would be left turns only, and then they could discharge during the second phase, which would be all the movements. You would indicate that it's controlled, the exit privileges of this link are controlled by traffic signal 5, for example, and it could discharge during phases, for example, 3 and 4. Okay, so that's the max you can do it. But those movements are for all the movements in that on that link. So basically, that link can discharge during phases 3 and 4, and all movements can discharge during 3 and 4. If you set it as negative signal 5, it tells it that the vehicles can make a right turn on red, which means that if it's right turn on red, they're going to look at the opposing flows and see if there's an acceptable gap for me to make my left turn. And if there is an acceptable gap, I'm going to execute my right turn and do it, I guess, without colliding with the vehicles that are conflicting with my movement. So this was not in your previous slides. I added this because you're going to need this for your project when you model your intersection, that the default in integration is whenever you add lanes, so let's say you're going from 2 lanes to 3 lanes, though the third lane is going to be added to the right. However, let's say you want to add a lane to the left because you have a left turn pocket lane, then what you do is you code the number of lanes on that specific link as being negative. So instead of making it 3 lanes, you're going to make it -3 lanes. And integration recognizes that with -3 lanes, I'm going to add that lane to the left as opposed to the right. So it would be a left turn pocket lane, for example. Any questions? Okay. So let's then, another thing that you have in your in integration is what we call the gap acceptance. And the gap acceptance is when you have a permissive movement, you as a driver are looking for a gap in the conflicting flow, or what we call the opposing flow, in order to safely execute your maneuver. So let's say I want to make a left turn and there's opposing through movements. So I will have to find a gap of a certain size in order to be able to make my movement. In integration, the default, which is based on empirical data, is that the critical gap for a through movement. So when would you have a through movement looking for a gap? When would the through movement be actually looking for a gap? Any thoughts? Right turn on red, but that's right turn. It's not a through movement. Is that correct, Sophie? So I'm saying a through movement and it's looking for a gap. So what you mentioned here will be a right turn. Jake mentions crossing a 1-lane intersection. So I'm not sure what do you mean by 1-lane intersection? Like what? Kevin mentions a lane change. No, so we're not talking about lane changes here, but it could be. So just to, I guess I'll mention this condition. This would be like a 2-way stop sign. So the drivers on the minor street have to cross the major street, but they have to search for a gap in the opposing flow. And so basically that will be a through movement that has to find a gap in the opposing flow, which is the main street traffic. And so basically it will be looking for a gap of 4.5 seconds. If the gap is less than 4.5 seconds, it's going to reject that gap. If it is 4.5 or greater, then it will accept that gap and will move to try to cross the intersection. So those are the defaults in integration. For a right turn, you decrease that 4.5 seconds by 0.5 seconds, which is based on empirical data. So basically the right turn on red is going to be searching for a gap of 4 seconds. For a left turn, you add 0.5 seconds. So you're going to make, instead of looking for a gap of 4.5 seconds, you're going to be looking for a gap of 5 seconds. And for each additional lane that you have to go through, so let's say you have a left turn movement that has to go through 2 lanes of opposing flow. So for the first lane, the closest lane to it, it will be looking for a gap of 5 seconds. For the second lane, it will be looking for a gap of 5.5 seconds. And then for the third lane, you'll be looking for a gap of 6 seconds. So every additional lane, we're going to be adding half a second. If you're at a stop sign, given that you have to accelerate from a complete stop, you add 1.5 seconds to that gap. Okay, so basically that takes into account the time it takes you to accelerate and so forth. Because in the left turn movements, a lot of times you could be moving, proceeding, and then you can just go to the intersection. Any questions on this? So this is what we call the critical gap that I'm searching for. The critical gap also decreases with time, and we found this when we looked at real data, empirical data, that the critical gap that a vehicle is looking when you're executing a maneuver decreases linearly with time. So what we're saying here is that drivers become more aggressive as they wait longer for a gap. And the default in integration is that after waiting for 2 minutes, you're just going to force yourself through and make the opposing traffic actually come to us, have to yield to you. So basically, so with time, so it starts, let's say you're looking for a gap of 5 seconds, you're making a left turn. It starts at 5 seconds and it will end after 2 minutes as being 0, but then you have a linear function between those two. So as time goes by, the gap that you're searching for decreases until eventually you're going to find a gap that you can use to execute your left turn. Any questions on that? And this time counter, or the stopwatch that starts counting your aggressiveness, starts when you reach a speed of a pedestrian, which is 1.2 meters per second, and that's where we consider that you are close to stopped. Okay. You can override these defaults. So these are the defaults in integration, which I would not suggest you overriding them unless you have evidence that the behavior of the drivers in this location are more aggressive, because we came up with these parameters based on empirical observations in the field. And so these are, I guess, typical driver acceptance behavior, but you can change that if you wanted to make the drivers more aggressive. For example, if you're in, I guess, my son studies up in Massachusetts, and the drivers there, I would say, are much more aggressive than the drivers here in Blacksburg. And so if I'm modeling the traffic there, I might go for some more aggressive behavior and change these parameters to make the drivers more aggressive, for example. So you can override this in 2 ways. One of them is in the link file, you code the first opposing link and the second opposing link. If you make it a negative, the first opposing link as negative, then that is the value. If it's negative, then the integration is going to recognize that's the value of the critical gap. And the second entry, once you code that as negative, the second entry becomes the decay time, which is the default 2 minutes that your gap that you're searching for is equal to 0. Now, if you don't want to override those parameters, you can just code 0 and 0 in those 2 fields, because integration is smart enough to recognize which movements are opposing my movement. So if it's a left turn movement, integration is going to try and identify all the opposing flows that will be conflicting with my movement. And those would be the through movement. So let's say you're making a left turn movement that's going towards the west. So it's a northbound approach, and they're turning left. So the opposing movements would be what? What will be the opposing movements of that left turn movement on a northbound approach? So I'm on a northbound approach and I'm making a left turn. Who would be opposing me? So I'm going to have to call names if no one is willing to volunteer here. So Kabul, any thoughts?
Would it be the left turn, but on the southbound?
So the left turn, no, the left turn on the southbound, they could execute their maneuvers without conflicting with one another. Is that correct?
Yeah.
So that would not be an opposing movement. So what would you think would be opposing movement to the northbound? I guess the left turn is on the northbound approach.
I guess it would be southbound, as Jake and Jody had messaged as well.
So southbound through movement, that's correct. And potentially it also could be the right turners in the southbound. So David Hong mentioned southbound through and right turn. So the right turn, it depends. If the road at which we are entering, so the left turners are going to enter a roadway which is going westbound, if that roadway is 2 lanes, the left turners could get into the leftmost of the 2 lanes and the right turners could get in the rightmost of those 2 lanes, and there would be no conflict between them. Is that correct? Now, if you're a driver, you might be reluctant to make your left turn when the right turners are turning right. Is that correct? Or I guess, how many of you would be, who would be reluctant to make a left turn into the leftmost lane of the roadway you're getting onto at the same time that the right turners are getting onto the rightmost lane? Would anyone?
I would be.
Okay. So, and I would be as well. Like, I would worry that the right turners could go directly into the leftmost lane. So what I do is I do it very cautiously. And we're going to get into this when we design the signals. You could actually consider that basically your opposing flow is maybe 1.5 times for the right turners. So basically you could consider half the time you would not accept that gap, and the other half of the time you're going to accept, you'd execute your maneuver. So it's really a judgment call for you when you're designing your signal timings, whether you think the drivers could make a left turn while the right turners are making their right turn. To be honest with you, I do it, but I do it very, very cautiously because I'm worried that the right turners might get into the left lane directly. Okay. The second way you can override this thing is if you use the opposing gaps.dat file. I would say for the purposes of this class, you don't need to worry about this, but what integration does is if it finds a file by this name, ops_gaps.dat, in the folder that you've indicated where your input files are located, it will read that file. If it doesn't find that file name, it will basically just use the default. Now, the advantage of this opposing gaps.dat file is that it allows you to be able to have variability rather than having, so the default is that everyone is looking for the same gap, like Kabul, myself, Jody, Jake, Jacob, Jackie, Eva, everyone is looking for exactly the same gap. If it's a left turn, we're looking for 5 seconds. If it's a right turn, we're looking for 4 seconds. If it's a through movement, we're looking for 4.5 seconds. If you use the opposing gaps, we could be different. I could be more aggressive than Kabul, for example. So you give it the coefficient of variation, and basically it will create either a log normal or a normal distribution of these drivers. So basically I could be aggressive and I would take smaller gaps for the same conditions that, for example, Kabul would be encountering. But each one of us is different because we're different people. So this opposing gaps allows you to add stochasticity into the system where you can have different drivers be more aggressive. Is that clear? And you can also have it different by different links, which is what you could also do in file 2. Any questions on this? On how you'd override this? We're going to get into the opposing flows later when we get into the signal timings, but for now, this is sufficient for the coding of integration. Okay, so a lot of times you would observe that a link can have, for example, certain movements that discharge during certain phases. The default way that you code an integration does not allow that. All the movements will be discharging during a certain phase, and the maximum you can have for the default is only 2 phases in which a link discharges in. Now, if you want to allow, for example, a protected left turn, then basically during a phase, it's only the left turners that can proceed to the intersection. The through and right turners have to wait. And let's say you follow that with the through left and right, where it becomes a permissive movement, and so basically now the left turners are discharging during 2 phases. In the first phase, they're in protected mode. In the second phase, they're in permissive mode. And so the way I would do that is as follows. In the link file, I would basically, so in order to activate this advanced format, if you recall in the link file, you have the first line is the title. The second line includes the number of entries that you have in your link file. So let's say I have 10 links in my link file, I'm going to have a 10 there. And then you have 5 scale factors, one for the length of the link, one for the free flow speed, the saturation flow rate, the speed of capacity, and the jam density. So if you make the number of entries in your link file negative instead of positive, so we said there were 10 links in my file. If I make it negative 10 instead of 10, integration will automatically recognize that this file is going to be in the advanced format. And it's going to be expecting that you're going to have additional entries in your link file, which are the ones here, which basically show so this is the link number. So if you recall, in the default one, you have just 3 entries: the link number, the first link that opposes it, the second link that opposes it. Here you have the signal number, not the link number, the signal number, first link, second link that opposes it. But in the advanced format, you have the signal number, and then the first phase, which you can discharge in, and then the movements that you can discharge. And this is a binary entry that allows, so basically, let me just draw here, you've got so if I put 1, 0, 0, that tells me that only left turn is allowed to be executed during this phase. If I do 0, 1, 1, then it says that the left turners are not allowed during this phase. So for this one here, the left turners are not allowed. However, the through movement and the right turners are allowed during this phase 4. And then given that this link can only discharge in 2 phases, all I do is I have to put a 0. So you have to have those entries. You have to complete the 4 entries. But in this case here, you don't have a third phase that it is discharging at. And the movements will be 0, 0, 0. And the fourth phase is 0. And the movements are 0, 0, 0. Any questions on how you'd code this? And this is what we said, that the number of links has to be negative. Any questions? Okay. We mentioned about the right turn of by coding the negative signal number. We mentioned this before. So before you never coded this file, which is the file 3. And basically you would, in this file, and maybe we'll just go to the actual file, to a sample one. Let me just go here. So this is a sample file here. So what you'd be coding is the same way we do in all the files. The first line is the title of this file. And then the next line, the second line, includes the number of traffic signals that you have in this file, and then the number of plans you're going to have in this file. So let's say, for example, I wanted to code a traffic signal where the signal timings change every 30 minutes. And so basically then, and I'm modeling for 2 hours. So given that it changes every 30 minutes, it will change twice every hour. And I'm modeling for 2 hours. So then I'm going to have 4 plans. So this one would be 4. And I would indicate the duration of of each of those plans as being 900 seconds, which is 15 minutes. Oh, no, sorry. We said 1800, which is the 30 minutes. 1800 seconds would be the duration of each plan. And then I'm going to have, for plan 1, I'm going to have the timings. And then I'm going to have this exact same batch repeated again, and then again, and then again, 4 times. But before each one here to be 1, before the next one will be 2, before the next one will be 3, and before the last one will be 4. Because this would be plan number 1, plan number 2, plan number 3, and plan number 4. Is that clear? And then for each of those plans, you give it the signal number, the cycle length, and if you're going to be changing the cycles, like integration can actually do what Synchro does. It can optimize the signal timings. And so if we're going to optimize the signal timings, you give it the minimum cycle that you're willing to accept and the maximum cycle that you're willing to accept. So it will search in this range for the optimum cycle length. Okay. Then the next entry is the offset. So that basically, if you recall, the offset was when will this traffic signal turn green relative to the upstream traffic signal. So here, this is the time at which it turns the offset of that traffic signal, the number of phases, the effective green time. So really, actually, this is the displayed green time, and the yellow plus all red time would be this 4 seconds, and then the displayed green time, and then the yellow and all red for the second phase. And then this 0 here is how often do you want to optimize it. If it's 0, means that I'm not going to be optimizing this traffic signal. I'm just going to allow it to run in fixed time mode. If it's 300 like here, that means every 5 minutes, I'm going to use the counts that I observed in the previous 5 minutes. And I'm going to assume that they're going to continue for the next 5 minutes. And I'm going to use those to come up with the best signal timings and then implement them for the next 5 minutes. Is that clear? Any questions? Okay, so let's go back to the actual text then, now that we've gone over. So this just describes the different things, optimization. So you can have by time of day, as we mentioned, you can have multiple plans. The offset, you can also optimize the offset if you were to set it as a negative offset. And the negative number would be the traffic signal relative to which you're optimizing the offset. So if I'm trying to do it in the eastbound direction, then I would use the traffic signal that is directly westbound of this traffic signal as the signal that will be used in order for me to compute the optimal offset of this traffic signal. Is that clear? And we mentioned that. That this is basically the traffic signal. Now, in integration, you can also have actuation. So you can have an actuator traffic signal controller where in the traffic signal number, you put a period, and then you indicate 5 entries, which are binary. So the default is it's 5 zeros, but you could then have it 10000, which means that you give it actuation for vehicle class 1. So this could be considered either actuation or transit priority. So you could just provide the actuation for buses only. So when a bus is detected, I change the signal timings for that specific bus. Or I could just have it as an actuated signal controller if I have them all ones, and then I allow it to change. It will detect the presence of those vehicle classes, and it will try to change the signal timings for those vehicle classes. Any questions? Okay. Another thing that will be important when you're doing your project is the lane striping file. And the lane striping basically indicates to the integration software if there are any striping constraints. For example, you might have a lane that is striped as left turn only. And so you would have to tell integration that this lane is left turn only, and the through and right turners should move out of this lane and use the other lane, which is a shared through and right turner. And so the way you would do that is you need to code in the lane striping file. Now, the lane striping file does 2 things. It allows you to do the lane striping, but it also allows you to restrict certain vehicle classes from the use of certain lanes. When do you think that will come in handy? The second thing, the second condition, when would that come in handy? Any thoughts? Bus lanes or carpool lanes, that's correct, Jake. So basically in this, you could actually model a lane that is only used for HOV vehicles, which are vehicles that have an occupancy of 2+ passengers, and you could dedicate that class to the HOV lanes. Or if it was a bus lane that is restricted only to buses, then you could allow that to happen. So you would force the other vehicles to, the other vehicle classes to not use that specific lane, okay? Whereas, for example, the buses or the HOV lanes, they could use that lane. In addition, they could use the other lanes. Now, vehicles are allowed to use that lane. So vehicle classes are allowed to use that restricted lane under certain conditions, because in integration, you can model incidents. And let's say that there were only 2 lanes, and one of them was for HOV vehicles and the other one was for regular traffic. And let's say an accident were to happen on the regular traffic lane that would block that lane. Under those conditions, integration would allow the non-HOV vehicles to get into the HOV lane in order to get to I guess, bypass this incident that's blocking the rightmost lane. Any questions? So let's get into, rather than describing this abstractly, let's actually just look at a file. Let me see if I have a file here. Yes. So this is how you'd code the lane striping file. Again, you'd have the title of the file. Let Let me just get my highlighter here. So basically you'd have the title of the file, which is the standard procedure that we have. Then you'd have the number of entries in this file. And then for each one of those entries, you're going to have the entry number. So it's going to be 1 through 17 in this case. The link number that you are coding this lane striping. So in this case, it's link number 15. The number of lanes on this link. So in this case, it's 3 lanes. And this has to be consistent with which file? What does this have to be consistent with? Where else do we code the number of lanes on a link? Jackie mentions in the link file, and you're correct, Jackie. So in the link file, we actually code in the number of lanes on that on that link, and so this has to be consistent. If you basically coded this 4 and in your link file it says 3, then you've got a problem. There's an inconsistency, and integration is going to give you an error. And then here what we have is the binary entry that indicates which movements are allowed on this specific link. So this, the first one is for the left turners, the second one is for the through movement, and the third one is for the right turners. So this is saying this is through only, this is through only, and this is through only. So let's show you an example here for 2-lane. This one saying that it's left and through, and this one is, the second lane is through and right turners. So the through movements are allowed to use both lanes, but the left turners are only allowed to use the leftmost lane, and the right turners are only allowed to use the rightmost lane. Here in this example here, you've got a left turn only lane and a through only lane, and then the third lane is through and right. So this is the leftmost lane, this is the middle lane, and this is the rightmost lane. So it's left, through, and this is shared through and right turners. And then, so depending on the number of entries, so here we've got 3 lanes, so you've got 3 entries. If you've got 2 lanes, you've just got 2 entries. What I like to do is I always like to have them aligned with one another. So even so, let's say here, I have only 2 entries. I make more spaces in order to have the second batch of entries, which are the, this is for the restriction of the certain vehicle types to a specific lane. So here, this lane can be used by all vehicles. This lane here cannot be used by vehicle classes 1, 2, 3, and 4, but can be used by vehicle class 5. So this, let's say, for example, this is a bus lane. So what we're telling it is this lane can only be used by the buses if they're vehicle class 5, and all vehicles can use the middle lane and the rightmost lane. So the buses can still use the middle lane and they can still use the rightmost lane, but more importantly, they're the only ones that are allowed to use the leftmost lane. And this would be similar to HOV lanes. So you'd have the HOV vehicles being vehicle class 5. So it's saying that this lane is an HOV only lane, and these other 2 lanes can be used by HOVs and SOVs, which are single occupancy vehicles. Any questions on the advanced coding and integration? So with this, you should be able to do the last question in your assignment number 6. You should have all the material that you need in order to finish your assignment. The lane bias, we won't get into this, but you can actually have lane biases. For example, an example of a lane bias is if you are driving on, for example, 460, and someone is getting onto 460 from Price's Fork, and you're in the rightmost lane and the traffic is very minimum, what are you going to do as a driver? Typically, what are you going to do? Any thoughts? So Jody mentions you move over to the left lane. That's correct. So that most drivers are courteous. And although I don't have to do that, given that someone is merging onto the freeway and I have the left lane beside me is empty, why not get into the left lane to make it easier for the driver who's merging? So most probably what's going to happen is I'm going to move to the left lane. So this lane bias allows you to say, for example, drivers are going to be courteous and move away from the right lane if they see other vehicles trying to approach. So they're going to move to the left lane to let them merge onto the traffic. If they can't find if the left lane is congested, then you're not going to do that because you can't do it, or because it's dangerous to do that. And so you're going to stay in the right lane. But if you can, you're going to do it. So that's how you could code that in integration. Any questions on this? For this class, you don't really need to code the lane bias. So I'm not going to go into the specifics of how you code this. Okay, so we're done with this lecture. So let's get into the next lecture. Any questions on integration coding before I get into the next lecture? Paige mentions, you mentioned the project. When will that begin? So very shortly, because I guess right now you can't do the signal optimization. So I would say we're going to start doing the project maybe not this coming week, but the following week. So you'd have about a month to work on your project. So we'll start maybe April I guess what is the coming week? April the 6th. So I just, now that you mentioned that, April the 6th, my understanding is a spring break. So we will not have a class on April 6th, but we might, so I might post the project maybe on April the 7th. Kevin asks, will there be a discussion board for integration, troubleshooting, and questions on the homework? I guess that's Sif, he does that. So I can mention that to him to do that. So that's something that the TA does. But you're free to send emails to either the TA or myself if you have any questions on integration or the homework. Any other questions? Okay, so let me get into the next lecture. So in this lecture, what we're going to do is compute the delay at an intersection. And delayed meaning that, so there are different types of delay that you can encounter at intersection. Today, we're going to look at one of those delays, which is called the uniform delay. And I guess, depending on, I would say today and Thursday, we're going to be doing the uniform delay. And then next week, we're going to get into the oversaturation delay, most probably. So in terms of the objectives of today's lecture, we're going to define the different components of delay to signalize intersection. We're going to compute the uniform delay to signalize intersection using what we call a microscopic approach. And then we're going to compute the uniform delay to signalize intersection using a more kind of macroscopic queuing theory approach. And then we're going to compute another component of the delay, which is not uniform. It's called the random delay. So basically, and then this is the reading material, but also the slide should cover everything. So I guess the first question is, what is the definition of delay? What is the definition of delay? Anyone know? Paige, any thoughts on what delay is?
The amount of time that is like you expected to get there sooner, and it's whatever time is not there when you thought you were going to get there.
Okay, so what you say is correct, but I'm going to try and rephrase it in a more scientific, I guess, way. It is the extra time that you will incur relative to the time it would take you if you were to travel at free flow speed. So you always have to have a reference. So delay cannot be done from one case. It has to have a reference, and the difference between those two cases gives you the delay. So here's an example of a vehicle trajectory. This is time. So let me just get my highlighter here. So the x-axis is time, the y-axis is distance. And this would be the trajectory of a car. So the first line here, the solid line, is the trajectory of the car if it were traveling at free flow speed. Then you have another straight line that is dotted. That is the trajectory of the car given that you're unable to travel at free flow speed because there are X number of vehicles on the roadway. And so they're forcing you to travel at speeds lower than your desired free flow speed. And so the difference between this black line and this dotted line is the delay caused by just my interaction with other vehicles on the roadway. But it has nothing to do with the traffic signal. So this is similar to what we would encounter on a freeway, remember? So if you're driving on a freeway and as you add more traffic onto the freeway, I become more constrained by the traffic and I'm forced to drive at speeds that would not necessarily be the speed that I would like to drive at. But because the vehicle ahead of me is traveling slower and because there are vehicles in the lane beside me, I'm unable to overtake that car and I'm forced to travel at the speed of that car, and so I'm forced to travel at a lower speed. So that's the difference between this line, the dotted line, and the solid line. Now, let's look at this other solid line. That's where I stop at a traffic signal. So the curvature here, so the straight line means I'm traveling at a constant speed. Curvature means that I'm either accelerating or decelerating, but the curvature, the curve that looks convex, which is this one, concave would be this one. This would give a deceleration. If the line is flat, it means that I'm completely stopped because I'm just incurring time, but I'm not moving any distance. The distance is 0, is that correct? Over this distance, over this time D1. Then after D1, there's a curvature which is convex, which means that I am accelerating, and then it becomes a constant slope. That means I'm cruising at a specific speed. So the difference between this line and the dotted line is the extra time that it takes me as a result of the traffic signal, given the number of vehicles on the roadway. But that is not the delay that we're going to be referring to. The delay is going to be D3, which is includes the time caused by the traffic signal and the extra time caused by the vehicles on the roadway that are also making me travel slower than what I would want to travel. Is that clear? Any questions? Okay. So basically, one, which is this one here, is called the stop delay because we're completely stopped. 2 is called the approach delay. 3, I guess is called the travel time delay, which is basically the total delay. And then 4, which is this portion, and this portion here would be, or 4 would be the acceleration deceleration delay, which would be the difference between, it'll be D2 minus D1. So D2 minus D1 would give me the portion of my delay that is a result of my deceleration and acceleration. Is that clear? Any questions? Okay. So there are three components of delay. One of them is called uniform delay, and the uniform delay is caused by the cyclic interruption of service during the effective red time. So I'm just going to read to you these, and then we'll discuss them. The oversaturation delay is caused by the accumulation of queues. So your demand exceeds your capacity or your supply, what you can serve. And so basically what happens in the oversaturation is the queues build up with time. So in the first cycle length, you're going to have a queue that does not get served in its entirety during the effective green time. And so you have some residual queue from the first effective green time that has to wait for the next effective green time. And then in addition to that, you still have a high demand. So you have those that have to be served from the previous time, plus the additional vehicles that are arriving that still cannot be served. And so you just keep on building a queue that builds with time. So if you live in Northern Virginia, I guess prior to COVID, I'm not sure what it's like now, whether things are back to normal, but basically what you'd have is this would be the typical conditions that you'd be observing in downtown Washington, D.C. During rush hour when when the demand exceeds the supply. Basically, that's what's happening. And then the third component is the random delay. And random delay is basically caused by the randomness in your system. And the randomness in your system comes from two components: the randomness in the arrivals of vehicles and the randomness in the saturation flow rates at which the vehicle is going to discharge from a traffic signal. So some drivers are more aggressive than other drivers. So there'll be, and also some vehicles are more aggressive than other vehicles. If you have trucks versus cars, the trucks are going to be slower and going to be taking up more space and going to accelerate at a lower rate and so forth. So let's go back now to the first one, which is the uniform delay. What do you think will be based on this description, when would you observe uniform delay? Any thoughts? Any thoughts when you do observe uniform delay? So Jody Schuler, any thoughts? So if you look at the, I guess David Hong says through movement. No, it's not through movement. I mean, it can be through movement, but that's not definition of it. So Jody, it says caused by cyclic interruption of service during effective red time. And it should not be oversaturated. So when would that occur? So Jacob says game day. I would say the opposite of game day. So the uniform delay will be observed when the demand is less than the supply. I would argue that on game day, the demand is greater than the supply. Is that correct? So you're going to observe oversaturation because you've got a lot of traffic. But uniform delay will be occurring, for example, in the off-peak periods where the demand is low. And so you can serve that demand easily within the green times, the effective green times. Is that clear? So uniform delay is not congested conditions. Oversaturation delay is when it's congested, and random delay is an addition on top of the uniform and oversaturation delay that occurs because of the randomness in the system. I think someone wanted to ask a question. Anyone wanted to ask a question? I guess not. Okay. So let's do an example illustration here. So we're going to solve this first microscopically. Microscopically means that we're going to be tracking individual vehicles. So let me actually copy this. Let's see. Let me just get out of the display mode. So let me just copy this. And let's go to OneNote, and we'll try to solve this in OneNote. It's ideally, it would be better to do it in a spreadsheet, but for now, I'll just copy this. But oh, actually, I need to stop share. And I need to, actually, what I'm going to do is maybe I'll go into Excel, and I will share my Excel sheet with you guys. It'll be easier to do it in Excel rather than do it. So my computer seems to be taking a long time to load Excel here. I'm not sure what's going on with my computer. So I might just, let's see how it. Okay, Excel is, okay, finally it loaded, okay. Let me just see here. Let's see here. Let me share the screen with you. Let me see here. Share. And I'm just going to scale this up so we can see it better. So I believe if you could just tell me the input parameters, the arrival rate V was equal to what? I'll just, what is the arrival rate? 900 vehicles per hour, was it? Let me go to OneNote here. And the saturation flow rate is 1,800 vehicles per hour. And they told us the following, that the cycle length is 60 seconds and the green time is 40 seconds. So let's, cycle length is 60 seconds and the green time, the effective green time is 40 seconds. Okay, and let's assume that we start off with a red time. So let's call it vehicle and arrival time and departure time. And then we can compute delay. So what we're going to do is we're going to track every vehicle and I guess compute its arrival time, its departure time, and basically from how would we compute the delay? The delay would be its departure time minus its arrival time. That's if we're looking at just the delay at the intersection caused by the signal indication. So how many vehicles will we observe during one cycle? How many vehicles will be observed during one cycle? Thoughts? So Ben mentions 15. So how did you, Ben and Jake, how did you calculate 15? So we calculated 15 as being the 60 seconds per cycle. So 60 cycles per hour. Sure. So basically what we're saying is we convert the 900. If you divide it by 3,600, that gives you vehicles per second, which will be a quarter of a vehicle every second. So it means every 4 seconds, you're going to have one vehicle. And if you divide the 60 divided by the 4, that gives you 15 vehicles. So 15 vehicles are going to be arriving during one cycle. So we know that we're going to have 15 entries. Is that correct? Because we're going to have 15 vehicles. Now, as long as we do it for one cycle, if there is no oversaturation, what's going to happen the next cycle is just going to be the same that happened the first cycle. Is that correct? It's just going to be whatever happens during any cycle is just going to be repeated during the next cycle. So all I have to do is solve it for one cycle, and I can multiply by the number of cycles. That gives me the total delay in a certain period of time. Is that clear? So let's say we don't know what time the first vehicle is going to be arriving, but let's say the first vehicle arrives at time 0, which can be changed if we want. So maybe actually let's insert a line here. Insert. So let's say vehicle 1 arrival. And I'm just going to make this into, and let's call this 0 seconds. And I'm going to make this one equal to that entry there. So if I wanted to change it, I could just change it. And then what I could do is, so there are 2 ways we could do it. We could just do it this way, where we just compute the departure time, assuming that it is red. So let me just actually do this. Insert, and let's say signal indication. So that's what is being shown on the traffic signal. Now let's say that basically, and I'm not sure if I'm gonna, this is right, mod 60. Actually, no, we can't do that because we have to have the time. So let's forget about this because this would be a more complicated way. So I'm just going to remove this column. Okay, so let's say it is red from time 0 to 20. Is that correct? Because we told you that it is effective green 40 seconds and the cycle length is 60 seconds. So the effective red time would be the 60 minus 40, which would be basically 20 seconds. Is that correct? So basically, given that it is the vehicle arrives at time 0, what is the earliest time that this vehicle can leave? What is the earliest time that this vehicle can leave? So Carver mentions 20, which is correct. So basically this 20 is actually what we could do is just make this equal to, it's the effective red time, which is basically the cycle length minus the effective green time, which would be the earliest time that this vehicle can leave. And so what would be the delay of this vehicle? It arrived at time 0 and it left at time 20. What would be the delay? So David and Katie mentioned that it would be 20 seconds. So yes, that's correct. So it'll be the departure time minus the arrival time will give me the delay for that specific car. Now, let's go for the next car. What time would the next car arrive relative to the arrival of the first car? Any thoughts? It should be the arrival rate, and I'm going to make that absolute, divided by 3600 plus the previous time that the other car, because the closest, actually, no, sorry, this would be the opposite. It should be 3600 divided by the C4, which is the headway. 3600 divided by the arrival rate will give me the headway between two vehicles. So given that they're arriving at a rate of 900 vehicles per hour, that means the headway between those vehicles is going to be 4 seconds. So vehicle number 2 will be 4 seconds after vehicle number 1. Vehicle number 3 would be another 4 seconds. So actually what I can do is just copy this cell, and it should give me the correct answer for the remainder of the cell. So vehicle number 3 would be 8 seconds, vehicle number 4, 12 seconds, and so forth. What is the earliest time that vehicle number 2 can leave the intersection? What is the earliest time? Eva, any thoughts? So David says still 20 seconds. Basically, if you say 20 seconds, David, then basically they'll be traveling on top of one another, which means there'll be an accident. So it cannot be 20 seconds. It has to be later than 20 seconds. Kabul says plus start delay. Not start delay. It will be plus what? So it has to be later than the time at which the first vehicle left. And this is one lane. So remember, this is one lane. So what should be the headway between any two vehicles that are leaving the intersection? The headway at saturation flow rate. That's correct, Jackie. So that will be the headway at saturation flow rate, which would be equal to what? That would be equal to 3600 divided by the saturation flow rate, which is this one here. I'm going to make it absolute. So it's C3 plus the time at which the previous vehicle departed. So it should leave at time 22. If I copy this, then this will give me the time at which they departed. And then I can just copy the delay. And that gives me now, there's something wrong with this equation, that we're getting negative delays. Is that correct? Why is that happening? Why are we observing negative delays? The reason we're observing negative delays, no, but we should, even if the queue clears, Kabul, it shouldn't be negative. We're saying, let's look at this vehicle number 12. We're saying that it's arriving at time 44 seconds, but it's leaving the intersection at time 42. Is that realistic? Can you leave before you arrive? No, David, that's not correct. We did consider the red time. The problem is we didn't consider the fact that after the queue gets served, the vehicles, we made them discharge at the saturation flow rate, but they only discharge at the saturation flow rate when we're discharging from a queue. After we serve the queue, what rate should they be discharging at? Kabul mentions the arrival rate. That's correct. So basically, I need to fix this equation. What should I do to fix it? It should be minimum of this and the cell beside it, the arrival time, or sorry, maximum. It should be the maximum of those two. Is that correct? I cannot leave before I arrive. Is that correct? So if I do this, then you can see now afterwards, it fixed vehicle number 12 that I leave at exactly the same time that I arrive. So basically, I'm just arriving at the traffic signal and leaving it instantaneously because I don't have to stop. Yeah, that's correct, Paige. The same as the arrival time. So now if I wanted to compute the total delay, what is the total delay equal to? All I have to do is sum up the delay of each car. Is that correct? And that will give me the total delay. So it's saying 110 seconds. We are at 9:16, but I just wanted to mention one thing, is that if I were to change the actual time at which the vehicle number one arrives at, instead of making it 0 seconds, make it 1 second, you can see now the total delay went down from 110 to 100 seconds. If I made it arrive at 2, it actually went down, let's see, it goes down to 90. So depending on when the first vehicle arrives during the red interval, the total delay of this system is going to change. The lowest value is going to be 90 seconds. The highest value is 110 seconds. I guess we've run out of time here, so I'm going to end it here. Any questions on this example and how we compute the delay microscopically before we end the lecture? Okay, so I guess there are no questions. So I guess we'll see you on Thursday. A reminder that Tuesday of next week, you do not have class because of spring break. And I guess good luck in your assignment. You should be able to do your assignment. And we'll continue the computation of the uniform delay on Thursday, hopefully. Goodbye, everyone, and have a wonderful day and the good rest of your week.